In the following problem, we're asked to use the definition of continuity and the properties of limits to show that the function is continuous at the given number a. We're given the function p sub v is equal to 2 times the square root of 3v squared plus 1, and the number that they want us to figure out whether it's continuous at is a is equal to 1. So notice that my function is in terms of v. So that means whenever I write my limit, it's going to be the limit as v approaches to, here specifically a is equal to 1, so it's going to approach to 1. Now I can just rewrite my function. So I can say 2 times the square root of 3v squared plus 1. So now looking at some of the properties of limits or some of the limit laws, I can look at one, specifically limit law 3, that allows me to take this constant that I have on here and bring it to the front. So I can rewrite this as 2 times the limit as v approaches 1, and then just rewrite what's left over, which is the square root of 3v squared plus 1. Now, another one of my limit laws allows me to take my limit and bring it into the square root. So when I rewrite this, I get 2 times the square root of limit as v approaches to 1 of, and I'm going to put this in parentheses, 3v squared plus 1. So now I can use another limit law, specifically the one between sums, limit law 1, and allows me to give my limit to both terms inside my parentheses. So I can write this as 2 times the square root of limit as v approaches to 1, and my first term on here is 3v squared. So I can say 3v squared plus my limit as v approaches to 1 of my second term. In this case, it's just 1. So now it's probably a good time for me to evaluate my limit, as I see nothing else that I can do in regards to properties of my limits. So when I go to evaluate my limits, 2, there's nothing to evaluate for. It's just a constant. But now let's write my square root. And when I go to evaluate the limit as v approaches to 1, all it's saying is take this v as 1 and plug it in wherever you see it v on here. So I get 3 times 1 squared plus, now one of my rules for limits says that whenever you take the limit of a constant, you just get that constant in return. So this just turns into 1. So I'm going to continue my work up here. So what's left over is 2 times the square root of, well, 1 squared is just 1. So I get 3 times 1 plus 1. And if I simplify further, I get 2 times the square root of 3 plus 1. And if I continue simplifying, I get 2 times the square root of 4. And so this can also simplify down to 2 times 2, which is my result of 4 for p's of 1. This is my answer. The next example wants us to use the definition of continuity and the properties of limits to show that the function is continuous on the given interval. The function they're giving us is g sub x is equal to the quotient between x minus 1 and 3x plus 6. And the interval they want us to show whether the function is continuous on is from negative infinity to negative 2. Typically, when we want to know any break in this continuity for a function like this, specifically a fraction, we know that we can't allow the denominator to be equal to 0, because when the denominator is equal to 0, then the function becomes undefined. So in this case, we take the denominator, so 3x plus 6, and we know it cannot equal to 0. So let's follow up with that notation, cannot equal to 0. And if we were to solve for our x value, then we would get where it would break this continuity. So let's do that. I'm going to subtract 6 on both sides to start isolating for my x. And I'm left with 3x equals to negative 6. And now to finally isolate by my x by myself, we divide 3 on both sides. And I'm left with x cannot equal to -2. So that means we can't plug in a -2 into my denominator. If I was to do that, let's write it right here, x minus 1 over 3, and plug in this -2 into my denominator, then I would be resulted with x minus 1 over -6 plus 6, and this would give us our indeterminate form, or undefined, of dividing by 0. So instead, let's build a domain of all the values that we can plug in to our denominator or our whole function in general. Those values happen to be any value from -infinity up until the point of -2. So we're going to put that in an interval. But it also includes all the values to the right of -2, from -2 to positive infinity. And now, if we go back to the main question, they want us to show that the function is continuous on this specific interval. But with the domain on here, we can recognize that this left side on here is exactly the interval that we're looking for. So in terms, -infinity to -2 is within the domain of G, and that is G is a continuous on the specific interval from -infinity to -2. That is all.